Sounds. We all know what sounds are, right? We've all seen a graph with crests and troughs, like a wave. But what exactly are particles, like electrons? I mean, they're called particles for a reason, right? Let's dive a little bit further. During the late 1600s, Newton thought that light was a particle, whereas his opponent Hooke thought light was a wave. But later it was found out that Hooke was actually right by Maxwell's equations, and light was indeed a wave, and the debate was settled. But a new phenomenon called the photoelectric effect came, and then stumped physicists once again. It wasn't until 1905 when Einstein came along and solved the photoelectric effect. But what exactly is a photoelectric effect? Let's take a look at an example. Imagine that the cardboard you see in front of you is a metal box and the hole is around where an electron would be. Let's say that you call this big rock photon 1 of a certain wavelength, and you call the small pebble photon 2 of a different wavelength. What scientists found was that only photons of a certain wavelength could kick out an electron from the metal box. In the example you see in front of you, the big rock does not do this. Since it can't penetrate the hole, it can't kick out an electron. Even if you try increasing the intensity, adding another big rock, it just does not do it. But pebbles, on the other hand, does exactly this. They go through the hole, meaning that they can kick an electron out. What Einstein found was that light traveled as a combination of a wave and a particle, called a wave packet, or a quanta, building off of a previous idea by the scientist Max Planck. You could find out the energy of a photon by using the formula E equals h times v, which is energy of a photon equals Planck's constants times the frequency of a photon. Whoa, light acts both as a particle and a wave? What? Okay, let's backtrack. After Einstein discovered this, he opened up a whole new field of quantum mechanics, where nothing was certain anymore. Everything was just probable. Let me give you an idea outside. Alright, so here I am outside with a small amount of water in a cup. And let's say that somewhere in this water there's a tiny particle of dust. Somewhere. Let's say I pour a lot of water in one spot, but I only pour a small amount of water in the other. Where is the dust more likely to be? It's not a trick question. The answer is obviously in the big pile where I poured more water, because that's how probability works. Similarly, in the quantum realm, nothing can be calculated for certain, only a probability of it being there, usually given by the square of this equation, the Schrödinger equation. But that's a topic for a whole new video. Let's say you're spinning something and you stop. You detect it here. Same thing happens with our eyes. Light is a wave moving in all directions, but we detect it as a particle coming from a single source. That's the wave-particle duality.